Welcome to lecture 18 of the course Marine Propulsion. The topic today is ship powering and efficiency components. So, the key concepts covered in today's lecture will be ship powering, the different power components which are associated with. So, the key components which will be covered in today's lecture are the different power components involved in ship powering analysis and the efficiencies of the ship powering system. So, if we look at the entire ship propeller system, which involves the power supplied by the main engine to the final power that is being absorbed by the propeller and the power required to move the ship forward. This is the depiction of the stern part of the ship. Here we have the main engine which provides the power to the propeller. Finally, the propeller is absorbing this power which is the delivered power and it provides the thrust for the ship to move ahead. So, PB is the brake power supplied by the marine engine. Now, this marine engine is connected to the propeller here. So, we have the propeller by a shaft and here we have a reduction gear which is required if the speed of the engine is higher than the propeller RPM, then a reduction gear is required. On the other hand, if we have slow speed diesel engines, we can get rid of this reduction gear component. Then thrust bearing is required, which basically transmits the thrust generated by the propeller through the shaft to the ship hull. So, the propeller generates a thrust which is taking the ship forward and this thrust force has to be transmitted to the ship hull, and this is done using this thrust bearing or sometimes called also thrust box for certain ships. And there are other bearings which are involved for this shaft, and finally this shaft passes through the stern tube at the aft end of the ship and connected to the propeller. PD is the delivered power that we have calculated before, which is given by 2 pi n into the torque Q of the propeller absorbed by the propeller, and PE is the effective power of the ship. So, PE is the final output power which is required by the ship to move forward with a specific velocity. Now, let us see how these power components are related to each other. So, the effective power PE is given by the total resistance of the ship multiplied by the speed of the ship, which is the effective power. Next, we have the delivered power, which is the rotational speed into the torque for the propeller. We say the QB, which is the torque in the behind condition, or we can write it as Q only. And on the other hand, we have the brake power of the engine. Sorry. Now, this brake power of the engine undergoes some losses as it is transmitted via the shaft to the propeller as the delivered power. So, between PB and PD, there is some loss which is due to the shafting, the gearboxes and the bearings in that case. So, this loss is generally in the range of 2 to 4%. So, we have an efficiency term calling shafting efficiency, which is basically relating the delivered power to the brake power. So, Pd will be Pb multiplied by the shafting efficiency. Now, Pd is the power which is delivered to the propeller and Pe is the effective power, which is the resistance multiplied by the velocity which is utilized by the ship to move forward. Now, the relation between Pd and Pe is important here because that is where the hydrodynamics of the ship propeller system will come into play. So, if we write Pe equal to RT into Vs, RT is thrust into 1 minus thrust reduction and Vs is velocity of advance divided by 1 minus wake fraction. This we have already deduced when we discussed hull propeller interaction. So, this becomes T Va into 1 minus T by 1 minus wake fraction. Okay. So, this is the expression for the effective power. On the other hand, if we look at delivered power, Pd will be 2 pi n into Q, which is Kq behind into rho n square d to the power 5. Now, what is Kq behind? If we assume thrust identity, then Kq behind can be expressed as a ratio of Kqo and eta r. This is 2 pi rho n cube 5 into Kqo by eta r, right. So, this is 1, 2. Now, the relation between the effective power and the delivered power is using all these propulsion coefficients, and the efficiency involved here is called the quasi propulsive efficiency. Eta d is called the quasi propulsive efficiency given by Pe by Pd. Okay. So, this is the ratio of the effective power to the delivered power for a ship. Now, using 1 and 2, we can write eta d equals T Va 1 minus T by 1 minus wake fraction divided by 2 pi rho n cube by eta r. Okay. Now, what is T? It can be expressed as thrust coefficient multiplied by rho n square d to the power 4. So, Kt into eta r will go in the numerator. Now, certain terms here will cancel out. So, we will have Kt by Kqo. Now, if we assume thrust identity, then the kT is equal to kqo, just like we have written the equation for kq as kqo by eta r, because we had already assumed thrust identity. So, I can write kT as kTo into, there will be a Va term here, Va by 2 pi So, we can write this as 1 minus T by 1 minus W into eta r into kT by kq in the open condition into Va by Nd. This Va by Nd is the advance coefficient J by 2 pi, right. So, here we can think of 3 terms. The first term is this ratio, the second term and the third term here. Now, 1 minus thrust deduction by 1 minus wake fraction is denoted as eta h, which is hull efficiency. Now, this is also not strictly an efficiency term. We call it efficiency because we are expressing the eta d as a function of different components. So, this component is 1 minus T by 1 minus W, which basically relates the thrust power of the ship to the effective power. So, if we see here in the equation for PE, T multiplied by Va, the thrust generated by the propeller multiplied by the advance speed, is basically the thrust power. This can be mentioned as PT, the thrust power. So, this thrust power is related to the effective power PE with this term 1 minus T by 1 minus wake fraction, where T is the thrust reduction factor. So, the propeller generates a thrust power, which is the thrust multiplied by the advance speed. Now, the effective power is the final power which is required to drive the ship forward at a specific speed. So, how is the thrust power related to the effective power? That will depend on the configuration of the ship in the stern region. That means, the shape, the line spline of the ship, especially towards the stern region, and also the propeller design. So, this is related to both the thrust deduction and the wake fraction. So, the effect of hull propeller interaction is very much expressed using this factor, which is the hull efficiency. Again, to reiterate, this hull efficiency is not an efficiency term. So, this is just the ratio of 1 minus thrust deduction factor by 1 minus wake fraction. Now, this hull efficiency can also be greater than 1, and depending on the value of wake fraction and thrust deduction fraction, it can be in the range of 0.9 to 1.2, it can have values. So, this hull efficiency value depends on the value of thrust deduction and wake fraction. Later we will see that for single screw and twin screw ships, the value of hull efficiency is typically very much different, because for single screw ships the wake fraction is very high. So, because of that we have a higher hull efficiency. Okay. So, what is the third term here? Kt by Kq into J by 2 pi in the open water sense. So, Kto by Kqo we have. So, this is the open water efficiency, eta O. This is the hull efficiency we have just seen, and we have eta R here. So, finally, we get the quasi propulsive efficiency eta D can be expressed as eta h into eta r into eta o. Okay. So, finally, if we want to relate the effective power of the ship to the brake power, that means the power generated by the engine, then we have P E by P B will be P E by the delivered power into P D by P B. Now, this first term is the quasi-propulsive efficiency depending on the hydrodynamics of the ship and propeller, and the second term is basically the shafting efficiency, because the delivered power depends on the losses that are incurred in the shaft. So, P D by P B is eta S. So, P E can be expressed as the brake power of the engine multiplied by P D into eta S, or in total P E can be written as P B into eta H into eta R to eta O into eta S. So, this expression relates the effective power of the ship to the brake power generated by the engine. Now, let us try to do a simple problem to evaluate these coefficients from the given data for a specific ship. In this problem, a twin screw vessel is given, that means there are two propellers, the design speed being 16 knots and the propellers are of 4-meter diameter. The operation condition is given with respect to the advance coefficient, and the kT and 10 kq values are given for that specific value of J. So, effective wake fraction, thrust deduction fraction and relative rotative efficiency values are also given as inputs here. The shaft efficiency can be taken as 0.97, which is typically related to around 3% losses in the shafting. So, we have to determine the propeller RPM, the brake power of each engine and the effective power of the ship. Okay. So, the propulsion coefficients are given and certain operation conditions are given. Based on that, we have to calculate the propeller RPM and powering. So, first we look at the inputs in this problem. The speed of the ship is given in knots, again we convert to meter per second, the diameter is given and J, kT, kq, these are given, wake fraction, thrust deduction, relative rotative efficiency, these are given as inputs. So, based on the given value of ship speed and the wake fraction, we can calculate the advance velocity. So, VA can be calculated based on Vs and wake fraction. Next, using the value of J, we can use this VA to get the value of N. We have already been given the value of the advance coefficient. So, if we know the velocity of advance VA, we can use this equation to calculate N. Okay. So, this gives the propeller RPM, the first part of our answer. Okay. Next, we will compute the powers. So, eta D is the quasi-propulsive coefficient given as eta H into eta O into eta R. Now, the hull efficiency eta H can be computed from the given values of thrust deduction and wake fraction. We get this value, here it is 0.978, slightly less than 1. Here the vessel considered is a twin screw vessel and hence the wake fraction is very low compared to a single screw vessel, because for a single screw vessel the blockage effect of the hull will be very much in the propeller plane, because it is at the central plane of the ship. But for the twin screw vessel, the two propellers will be at the two sides where the velocities in the wake field will be higher and hence the wake fraction will be low. Eta O can be calculated from the given values of Kt and Kq with the J, and finally we can calculate the value of eta D, which is the total quasi propulsive coefficient which comes from the hydrodynamics of ship propeller interaction. Now the delivered power can be calculated for each propeller. So Pd is the delivered power based on the torque coefficient and relative rotative efficiency. The delivered power to each propeller can be calculated here, and based on the shafting efficiency of 0.97 which was given in the problem, the brake power of each engine can be computed from the delivered power. So Pd by eta S will be the brake power. Now in this case we have two propellers, so there will be two engines. So the brake power of each engine will be calculated from the delivered power from each propeller divided by the shafting efficiency, and finally the effective power, which is the power required to drive the ship forward, which is this is the effective power given as RT multiplied by Vs, right. In this problem we did not know RT, okay. So we are calculating the effective power from the delivered power side using the quasi propulsive efficiency eta D. Now the delivered power that has been computed is for each propeller, but the effective power is for the entire ship. So we have two propellers, so we have to multiply the delivered power with the number of propellers, which is 2 here, and also the quasi propulsive efficiency to get the effective power. So this is the value of the effective power of this ship. So these simple problems on propulsive coefficients and powering can give some idea on how to evaluate the powering performance of a ship based on some operational conditions. So this will be all for today's class. Thank you.